Hi, everybody. I guess I'm a couple minutes late here, but this is my fourth live stream, my fourth live stream on Dave's Math channel. And today I'm going to talk about magic squares. And I didn't quite have as much time as I would have liked to prepare this video, so this is probably going to be a lot shorter than an hour. May even be shorter than a half hour. I'm not sure. But anyway, I'm going to talk about standard magic squares. Sometimes they're just called magic squares. And there's a picture of a 7 by 7 magic square. I'll show you how I can construct such a magic square by the end of this live stream. But anyway, let's get started. So first I have to define what a standard magic square is. And there's other types of magic squares that aren't standard. But sometimes people just, when they say a magic square, they really mean a standard magic square. So what is it? A standard magic square is a matrix. It's a square matrix. In other words, a square grid of numbers, n by n. So we call n the order of the magic square. And n can be any positive integer except 2. Turns out there's no 2 by 2 magic squares. That's pretty easy to prove. But anyway, a standard n by n magic square, or standard magic square of order n, if you like, is just a matrix with all the numbers from 1 to n squared. Because it's an n by n grid, you can fit all the numbers from 1 to n. I think I said 1 to n here. I meant all the numbers from 1 to n squared, with each one occurring exactly once. And also, the reason it's called a magic square is because every row, every column, and both of the two long diagonals of the square all add up to the same number, the same sum, which is called the magic constant of the square. And it's pretty easy to derive a formula for the magic constant. I mean, it's really just the sum of all the elements of the square divided by n. Uh, and we know how to sum all the numbers from 1 to n squared. That's just n squared times n squared plus 1 over 2, or if you like the nth squared triangular number. That's a well-known formula for adding all the numbers from 1 to m, the nth triangular number, which is m times n plus 1 over 2. So if we just divide that for n squared by n, we get the magic constant, which is, I'm calling it k of n here. That's just n times n squared plus 1 over 2. So that's a formula for the magic constant of any standard magic square. And here's a little table of the values for n going from 3 to 10. So the 3 by 3 is the simplest non-trivial case. And that has a magic constant of 15. And then after that, we've got 4 by 4, order 4 magics where the magic constant is 34. They grow pretty quickly. For 5 and 65, by the time you're up to order 10, it's already 505. Um, and it turns out that there do exist magic squares of every order, like I think I said, except 2. Um, and then when n equals 1, there's a trivial case. That's just a square with a single element 1, so which magic constant would be 1, but we don't really care about that one. Okay, so what's the simplest magic square? That's the 3 by 3, which is also called the Lo Shu square. This was discovered a really long time ago in ancient China, around 2800 BC. And I think there was a legend from around that time. That's why there's a picture of a turtle here. The legend is that there was a special turtle that had this Lo Shu square written on its shell, on its back. And I think it had some kind of mystical religious significance for the Chinese. I know they had a lot of numerology connected with this magic square. And they didn't have, the Arabic numerals we do today. The modern version of them is shown on the right. And then the version on the left, I guess they used, little patterns of dots with that number of dots. So The top row is 492 if you have the dots, and then you got 357, and then 816. And this turns out to be the unique 3 by 3 magic square up to rotations and reflections. There's actually 8 of them because there's 4 ways you can rotate the square, and there's another 2 ways you can reflect it. So you get a total of 8. 4 times 2 or 8. But the standard way that the Chinese represented their Lo Shu square is shown this way. Top row is 492, middle row is 357, and the bottom row is 816. And an easy way to remember this, whenever you have a magic square of odd order, the number in the middle always goes in the middle of the square. In this case, this is 5. 5 is the number in the middle of all the numbers from 1 to 9, 1 to 3 squared. So 5 goes in the center of the square. And then the other odd numbers go on the middle of each of the extreme rows and columns. So we've got the 1 on the bottom. It's probably easy to remember that you start with a 1 on the bottom, the middle of the bottom row. And then the one that has to go opposite that is 9, because that's the only number left, such that the sum of this row, of this column, is 15. And then the remaining odd numbers are 3 and 7. And by convention, we put 3 on the left, and that forces 7 to go on the right. And then all that's left are the even numbers, and the even numbers go in the corners. And I think the only one of those you have to remember is 2 goes in the upper right corner, and that forces 4 to go to the upper left, and it also forces 8 to go in the lower left and 6 in the lower right. So that's how you would construct a Lo Shu square, um, and that's what it is, and that's the oldest known magic square, and not a difficult one to construct. Um, and then after that, I guess there were no magic squares that were known for a really long time. I think the next one wasn't even discovered until the Middle Ages. 4 by 4. 4 by 4s are a lot harder. It turns out, I mean, there's only one magic square of order 3, up to rotations and reflections. For order 4, there's already 880. And I think that they were all constructed at some point during the Middle Ages. But there was a very famous Renaissance man, I guess an artist, polymath, like a lot of Renaissance men were. He was a German artist and I guess also a mathematician. And he actually constructed probably the most remarkable of all the 880 4 by 4 standard magic squares. It's now called Durer's magic square, and he first illustrated it in this work of art he made, which is shown on the top right. This is called Melancholia 1, and there's a lot of references to math in this painting he made. I mean, there's this geometric figure of geometric polyhedron, top left side near the middle, truncated. I think it's a truncated sexahedron or something like that. He's also got some other references to math in this picture. He's got a scale and he's got an hourglass. And, but one thing in this diagram, in this painting of his, is his magic square, and the angel on the right is actually holding up this magic square right above his wing. And there's a little inset of the magic square on the bottom right. And you can see the numbers in it. And, you know, one interesting thing about this square was that he used the year he made it, 1514, for the numbers in the middle of the bottom row of the square. You can see the 15 is the second from left on the bottom, and then the one right next to it was 14. So that was the year he painted it, 1514, and that's his magic square. And you know, the thing that's really remarkable about this magic square is that it has a lot more magic sums. It has a lot more sets of 4 numbers that add up to 34, the magic constant. I mean, it has all the rows, columns, and the 2 long diagonals. That's what's shown in the top left. I don't know how well you can see this, but I think there's something like an additional 40 sets of 4 numbers, all of whose sums is 34. For instance, the 4 corners add up to 34. The 4 numbers in the middle add up to 34. That's what's shown in the second of these diagrams. And then if you take these rectangles, you take, say, the second and third element of the first and fourth column, those add up to 34, as do the second and third, the second and third elements of the top and bottom row. And then also, if you looked at each group of 4 numbers in each quadrant of the square, the first 2 rows and columns, or any 2 rows and columns in the corner, those all add up to 34. You can see all the patterns. These all add up to 34. Every one of these patterns shown. And I don't even know how many there are. I think there's 40 in addition to the standard. So pretty amazing magic square. And anyway, that's the Durer magic square, the 4x4. And yeah, this is gonna be a short live stream tonight. Sorry about that. I didn't really spend enough time preparing it. I could have said a lot more about magic squares, but I'm just gonna finish by telling you about a way to construct an arbitrary magic square of odd order. And this was first described in 1693 by a French diplomat, pretty famous French diplomat. He was also an amateur mathematician. His name was Simon de La Loubere. I think he worked for the King of France at that time. But he actually came up with a method for constructing an arbitrary magic square of odd order. It has to have odd order. It wouldn't work for even order. But this illustration shows you how you would construct it. For instance, how you would make a standard 7x7 magic square using his method. So the way you do this, you start on the top row. You write a 1 in the middle of the top row, and now what you do is you keep going up and to the right, but wrapping around if necessary. So in the first step, you have to wrap around. You can't go above the top row. You end up in the bottom row, and then you also end up 1 column to the right. So I think you can see there's a 2 in the bottom row in the 5th column, and then you keep going along, up and to the right. So you put a 3 in the 6th row, 6th column, 4 in the 5th row, 7th column, so on. Now you have to wrap around again. You put a 5 in the 4th row, 1st column, and then a 6 in the 3rd row, 2nd column, and the 7 in the 2nd row, 3rd column, and then you're back to where you started at 1. But once you get back to your started, now you have to jump. You jump down, I think. Yeah. So you put an 8 right below the 1. Is that the way he does it? I can't remember what the 8 is. No, actually, you go below the 7. So you can't go to the 1 because that's already taken. So 7 is the last step going up and to the right. So now you just go 1 step down and you put an 8 there. And now you do just like what you did before. You go up and to the right until you're done. So the last number you're going to write in that case is 14, which is one square below and to the left, the 8. And now since you can't go any further, you put a 15 right below that one. Keep going like this. And you keep doing all these steps until you're done, until you've filled in the whole square. And the last number you're going to write down, if you do this, is 49, which is the last number of the square. And lo and behold, this turns out to be a magic square. Yeah, and this doesn't just work for order 7, it works for every odd order. It'll also construct the Lo Shu 3x3, construct 5x5, 9x9, 11x11, whatever you want. It doesn't work for even. For even order, there is kind of a trick to I don't know any general method for general even order, but I do know a method which I didn't have time to prepare, show you how to do it. But it's actually a very easy method for constructing a magic square of order 4. And I'll just tell you in words on how to do it. So what you want to do is first you just write a square with all the numbers from 1 to 16, just write in lexicographical. You're like 1 through 4 on the top row, and then 5 through 8 on the second row, going left to right, 9 through 12, 13 through 16. Do all that, and then what you do is you erase all the numbers along the main diagonals, the long diagonal. That's going to leave you with the 8 numbers in the middle of each row and column on the edge of the square, and then you count backwards to fill in the other numbers. You write a 1 in the bottom right and bottom row right column, and then you keep counting backwards. And you would put a 4 in the bottom row left column. You just keep counting backwards and filling in the numbers that you're counting that aren't taken. And if you do that, you will get a magic square. It won't be the Durer magic square, but it is a magic square of order 34. You can check that yourself. I mean, of order 4 with magic constant 34. And one more thing I think I should mention, since this is a short video. One very famous man who was interested in magic squares. You might be surprised by this, but Benjamin Franklin, it turns out. He dabbled in math. He was an amateur mathematician, and one thing he was really interested in was magic squares. And he constructed a really remarkable 8 by 8, not exactly magic square. It's called a semi-magic square. Uh, but it has really remarkable properties, kind of like Durer's magic square. It has all these combinations of 8 numbers that add up to the magic constant, which is 260 in that case. Uh, maybe I think I have to do another live stream on magic squares because I didn't say everything I want to say about them tonight. Anyway, apologize for that. Like I said, this was a short live stream tonight, but magic squares do seem to be a popular topic, popular math topic, popular recreational math topic. Anyway, it's not something you usually learn in school. It's not something with a lot of obvious applications, but it is something that I think is a lot of fun, and it has intrigued mathematicians for most of history. So anyway, so that completes my live stream for tonight on magic squares. Thank you for watching. Long live math, and I'll see you guys next.